My name is Luiz. Today we're going to talk about blockchain. So the purpose of my talk is I'm going to try to highlight the purpose of essentially what a blockchain is, and we're going to talk about what's a block and what is a transaction. And this is going to be a lot of code, so I'm going to try to go through it as quickly as I can so that we have some time at the end of the talk, so I can answer some questions if you have some questions. Let's begin. So, what is a blockchain? Basic understanding is it is a distributed, append-only ledger that is continuously growing. So, in the case of Bitcoin, which is the famous implementation of the blockchain, every 10 minutes or so, a new block is added to the longest chain, sort of appending the existing records that are on the chain itself. Put a little image right here, sort of describing how the blocks and the chain come together. And essentially, every block has a set of properties, and they're linked to other blocks, thereby forming the blockchain. And the specific property of the blockchain that's pretty interesting is that they're linked not by pointers, but by hash pointers. And that is going to come into play once we start looking into the code. Basically, whatever new block is, whenever a new block is created, it is referencing a parent block by the hash of that previous block. So let's look at what a block is. A block is essentially just a data structure that holds transactions. And for the purposes of our code example, these are going to be the properties that we're going to assign for our block. We're going to have a previous hash, just referencing the previous block on the chain. Timestamp, pretty self-explanatory, is just the creation of the block, the time, the approximate time. There's a transactions property, which is just a list of all of the transactions that are appended to the blockchain and sort of combined into this block. There are two properties one is called the nonce and the other one is called the hash, and these two come into play when we talk about mining, which is the process of solving a puzzle in order for you to be rewarded with the chance of adding a block to the existing blockchain. So let's look at what a transaction is. Transactions are in the block, and a transaction, for the purposes of our example, it's only going to have three properties: the from address, a to address, and an amount. The amount is just a number of coins that are spent, and it basically dictates from one person to another person, they're sending 50 big skydive coin. The example I put here is Bob pays Alice 50 big skydive coin for a slice of pizza, depending on how much are 50 big skydive coin. This could be a cheap pizza or very, very expensive pizzas. The requirements that I'm going to give for us to work on today is we're essentially just going to build a very rudimental blockchain. There's not going to be any decentralization. There's no peer-to-peer network. I'm only going to highlight the properties of how a block is created and how a block is appended into the blockchain, and then the process of using proof of work, which is something I'm going to talk more about later, which basically just makes it so that honest nodes are on the network are always creating blocks that have valid transactions and appending into the blockchain. In a real blockchain where everything else is distributed, then there would be some sort of consensus in order to verify that the block that's being promoted is indeed a valid and true block. So let's start looking at some code. All of this is going to be in JavaScript. It's just easy to understand, at least for me. I'm going to be using some ES 2015 syntax. If you do have any questions, just let me know later on, and I'll be happy to answer them. In here, we're going to create our block class, and then, like I said before, we're going to have our timestamp, our transactions list, and a previous hash. And then those two properties that I mentioned that will come into play when we talk about mining. One of them is the nonce, and then the other one is the hash. So let's look at this generate nonce method that I created here. Essentially, what I'm doing is creating, the nonce is basically going to be, for our purposes, a 32-bit string of random numbers. And where this comes into play is when we are generating the hash for the block. We need a way to change something on the block that will help us create a hash that is below a certain target. I'll touch more upon that later, but the purpose of this here is just playing a guessing game of trying to find a combination of numbers and strings that will help me generate a hash that will produce a valid block. All I'm doing here is I'm pulling in the crypto module from Node, and it gives me this random bytes method that I give it a length. For our purposes, it's just going to be a 32-bit length. And then I output the string in the hexadecimal notation. So let's look at the calculate hash part. If you remember up top, we have this, there's a hash, and I call calculate hash. And the calculate hash is a pretty interesting method, so that, again, I'm using the crypto module, and I'm just creating a hash for SHA-256. And then, in order for you to hash this block, you pretty much take all of the properties of the block, with the exception of the hash. And then you feed it, you concatenate it, all of these values, and feed them into this hash function. The hash function is basically just a mathematical formula that, given an amount of input, will output a specific length. In our case, is SHA-256. And it's going to be in hexadecimal notation. So I'm taking in the previous hash, the timestamp, JSON string defining all the transactions, and then taking the nonce, calculating the hash, and then outputting the string in hexadecimal. So like I said, this all comes into play when we're talking about mining, and the mining game is essentially trying to solve a puzzle. The puzzle, for our little example, takes in a difficulty, which I'll touch upon later again. This comes from the blockchain itself. But given a difficulty, we're going to create a target, and for our purposes is going to be a string of length difficulty. So in our example, difficulty is going to be 3. The more I increase the difficulty, the more hashing power, the more computational power it's going to require in order for me to generate a valid block that can then be appended into the blockchain. For the sake of time, I'm setting it to 3, and it makes it run a lot faster. If I just put it 4, it starts running way slower. The method here, all it does is it checks to make sure that the beginning of our hash is below that target. So meaning if the hash does not have the 3 zeros in front of it, then try again. And what we're going to do is we're going to generate a new nonce and then calculate the hash based on that nonce. And the nonce here is the only property that we can change, because we wouldn't be able to change the transactions or who sent money to whom or any of that stuff. We don't want to touch any of that. We just want to pass all of that information into the hashing function and then change the nonce so that we can try to figure out if we can generate a new hash that meets our difficulty or is below our target. So creating the blockchain, here I created a blockchain class, and our blockchain is going to have a chain property, which is going to hold all of the blocks that are on the blockchain. And I talked about the difficulty. We're going to assign it to 3. And we have these 2 other ones. The pending transactions is essentially, if you think about all of the nodes that would be on a network, they're all constantly broadcasting transactions. They're then picked up by special nodes, which are called the miners. And the miners are just concatenating all of these transactions that they're receiving from all the nodes that are connected to it. And based on those pending transactions, they'll try to computate the hash of a new block in order to be rewarded a mining reward. And in our purpose, we're just going to reward whoever finds a new block 100 coins. I put a comment here to talk about the Genesis block, which is the very first block on our chain, and it's almost always hard-coded. If you want to take the time to go into the block explorer, you can actually look at Bitcoin's very first block, which is the Genesis block, and there's a pretty cool message in there about bank bailouts. So let's start putting some stuff together. So the Genesis block is almost always hard-coded. So what I'm going to do here is I'm going to require the block from our source, and then I'm going to create this method called create Genesis block, and all it does is it creates a new block, and I'm passing today's date. And whenever this blockchain gets instantiated, the first block is always going to be there. So we talked a little bit about the difficulty and how it is used to enforce the proof of work, and how proof of work is a system that ensures that the network is working properly, because it keeps honest nodes expending computational power. In order for you to do that, you have to pay for electricity. You have to buy machines. You have to spend money to then put your machine to work on the stuff. And this feeds into sort of the system that makes sure that the whole network is stable. You spending the time to expend the computational power to generate a new block will then make sure that the value of the coin stays strong, which then rewards other people to then join the network for them to reaping some of the benefits of the valuable coin that has been generated. And like I said, a valid block must have a hash that is less than the target, and the target is determined by the difficulty. In Bitcoin's case, this is sort of, it self-adjusts so that given the amount of hash power that is on the network, at most there's only one block being generated on average every 10 minutes. If more hashing power is introduced into the network and a block gets generated in less time, the difficulty is then changed automatically so that the next time, given the new hashing power, the block is going to be generated in the 10 minutes. Continuing on with our example here, I added these 2 methods. One is add block, which given a block, it just appends it to our chain property, which is our blockchain. And then the helper method for adding the transactions that are being broadcasted by the nodes and appending them into the pending transactions array. Those 2 will come into play when we start mining again, and we'll talk more about the mining process here in a second. First, let's talk about the transactions. Like I said, the transactions for our use case is very simple. We're just going to have a from address, a to address, and an amount. It's pretty self-explanatory. We're not going to be dealing with too much stuff. All of these transactions are just going to be broadcasted into a miner node, and the miner is going to then take all of the pending transactions that they have and try to generate a new block. So, mining pending transactions. This is where it starts getting really interesting, because in order for you to be rewarded for generating a new block, you have to create a block, and here we're instantiating a new block, passing today's date, and whatever the list of pending transactions that this node might have at that time, as well as getting the last block that the chain has and its hash. If you remember, on our block class, we have timestamp, transactions, and then the hash of the previous block, so that we can create a pointer to the parent block. And so we're going to attempt to mine here, passing in the difficulty. Once the block is mined, we append it to the blockchain, and then we reset the pending transactions. Resetting the pending transactions is just a helper method that sets the pending transactions to an empty array. And then we create the reward for the good, honest nodes. And this transaction does not have a from address. It's sort of just creating value out of nothing. Yeah. But this is what lends value into the system. So, given the miner's address and the mining reward, we create a new transaction. But this transaction does not get added into the blockchain until the next time a block gets generated and then added to the blockchain. So then, if you remember, the mining of the block takes in the difficulty and then creates this target, and then keeps trying to generate the nonces and calculate the hash until we meet the target number. So in our example here, I'm going to be using the crypto module again, and all of this, all I'm doing in these, from line 7 to 17, these 10 lines, I'm just generating addresses. I could have just put strings, but I wanted to make sure that I had a good grasp on the crypto module. And all I'm doing here is generating key pairs and then getting the public key for the key pair that I generated. This just helps with digital fingerprints for the miner, Alice, and Bob. And we're getting the public key in hexadecimal value so that we get the sort of an address. And I only did this so that when I run the examples and we start looking at the addresses and all of this stuff, it sort of looks similar to what you would encounter on a production-ready blockchain, and especially if you start messing around with cryptocurrencies. So going forward, I'm going to bring in our blockchain, our transaction class. We sort of set up this the wallets, for lack of a better term. We instantiate a blockchain, and then here we're saying that a miner joins the network. Again, this is not going to be a pure peer-to-peer implementation, just for the sake of time. But think of this as a node goes online and says, hey, I want to mine. It's usually a specialized machine. Then suppose that the miner has gotten some money, some value, and then created a new transaction, paying Bob for some widget, sending 100 coins. Then Bob pays Alice for some other service, and that's 50 coins. and then the miner tries to solve the puzzle. Meanwhile, all of these transactions are being broadcasted to the nodes and added to the pending transactions. And then we're going to mine and then check the balances later. So if I run this, you see that we have one block mined, it took about 40 milliseconds, and the second block, 10 milliseconds. And then we see here the balances of the wallets. The miner has 0, Bob has 50, and Alice has 50. And those are the 100 coins that were generated when the miner joined the network and started mining blocks. And then let's look at that get balance method from the previous example. All we're doing here, since our transactions are just going to have a from address and a to address, I'm going to loop through the blocks in the chain and then get the transactions. And from those transactions, I get the address, the from address and the to address, and I either decrease the balance or increase the balance and then return the full balance at the end. The get transaction is pretty self-explanatory. You're just diving into the transaction property of the block. So then let's talk about how a double spend attack might happen. And the double spend is essentially, so say the miner paid Bob here 100 coins, and then later on the miner goes, no, actually I'm just gonna send Bob 50 coins. Meanwhile, the chain has already been created and the block has been appended to the chain. What one could do is create this rogue transaction. Essentially, I'm going into the chain, grabbing the block at index 2, which would have been the miner sending Bob the 100 coins, and I get that transaction. From that first transaction, I change the amount from 100 to 50, and then we're going to check the balances. If you remember from the previous example, the miner's balance should be 0, Bob's should be 50, and Alice should be 50. So when I run this, oh, something went wrong, right? The miner's wallet is 50, Bob's wallet is 100, and then there's 50 in there. Things are not looking right. In order for you to sort of understand or make sure that the chain is always valid, there are these methods that all of the blockchains have in order to validate that we are in a state that is valid. So for our example, I'm going to create this chain valid method, and I'm going to loop through the chain, skipping the genesis block, because the genesis block does not have a previous block. And so I'm going to check that the current block and the previous block, so the current block, the hash of that block has to match the calculated hash. So I calculate it again, given the parameters that I have, which is I have access to all of the information that's on that block plus the nonce. So I can do the computation as well, which means proof of work. If that's not equal, then the chain is not valid. Or if the previous hash of the block that I'm checking, the current block, is not equal to the previous hash of the block that's before it on the chain, we know that something went wrong and we return false. And then for the purposes of our little chain, if those two are true, or if those two don't evaluate, then we return true. Let's take a look at the same example of the double spend, but check to see if the chain is valid or not. And yep, sure enough, the chain is not valid. So then you might be thinking, well, if the chain, if I change something and then I can just calculate the hash again and then set that hash to the new hash of the block that I'm trying to mess around with, Well, how does that work? So here I'm taking the block and calling a roadblock, and then getting the transaction, changing the amount, calculating the hash, and setting it to the hash property of my roadblock. See how that plays out. Nope, the chain's still not valid. And that is because we may have calculated a new hash, but that hash is no longer pointing to the hash that comes after it. So meaning that the previous hash has to match. So you may say, well, why don't I change the block, my block, and then every other hash after it? So in order for you to do that, you would have to then calculate the hash of your block, any other block after it, thereby changing all the nonces, having to expend all of the computational power again. In order for you to do that, like I said, you have to get the chain, and then from your block that you're changing, change the hash property and the previous hash property for all of the blocks after it, and then mine them again. So when I run this, you see that the chain is valid, but look how many blocks we had to mine in order for me to renege on 100 coins that I sent to Bob if I were the miner. This is where the proof of work comes in, is that it becomes infeasible, not impossible, but infeasible for you to then change something that has been previously added to the chain. The longer the chain has been validated and is on the block, on the blockchain, the harder it becomes for you to then change something on the block and then make your change propagate throughout the valid chain. So there we have it. We created a simple blockchain. We mimicked all of the interactions between the nodes on the network. We had the miner, we had Bob and Alice. They were all doing transactions with each other. We showed how a double spend attack might happen and how the proof of work would help prevent this double spend attack. And then, like I said, we had a couple of caveats where, for the sake of time, this presentation did not go too much into the peer-to-peer network or how the consensus algorithm really works. Those are pretty extensive topics, and I would love to talk about them. Maybe I'll do a presentation at the Missoula meetup on those two subjects. If anybody's from Missoula, you'd be welcome to come. Does anybody have any